다 들리나요? So can you hear me? Would you say yes or maybe nobody can hear? Okay, good. So I think there were some issues in setting up these Zoom sessions. I did exactly the same thing as what I did before, but it turns out I have to grant the permissions. I mean, I have to allow the students to come in if they want. I mean, if I want them to join this session, which is not exactly what I intended. So I'm gonna wait about 5 more minutes before starting the session. 한글로 잠깐 얘기하면 원래 제가 아무것도 안 하고도 학생이 다 들어올 수 있도록 셋업을 해놨는데 이상하게 그렇게 안 되네요, 오늘은. 그래서 한 5분 정도, 5분 정도 기다려서 더 조인할 학생들이 있으면 받고 그러고 시작을 하겠습니다. So we will wait 1 more minute. Okay. Okay, so let's start today, and welcome to CS520, Theory of Programming Languages. And this is a graduate level course on programming languages. So, there's just some difference between this course and the undergrad programming language course. This course emphasizes a lot more on the denotational semantics, which is also emphasized quite a bit in the textbook that we are using. Also, the course will focus more on the mathematical analysis. So we are not proving many deep theorems, but instead we're gonna use quite complicated notations. Well, quite complicated concept from the mathematics, and that's somehow that is needed because the programming language is not a simple object. Okay, so let's get started, and let me share the screen. Okay, so as I said, this is a course on theory of programming languages. And so let me just set things up a little bit. Okay, so I'm Hong Seok Yang, and we will have, I'm gonna teach the course, and then there will be 2 TAs for the course. And as I said, the main question that we try to address in this course is about how to analyze existing programming languages formally. So by existing programming languages, I mean their constructs, like some languages, most of the languages have a while loop, for loops, and so on. And some languages have support high order functions very well. And it has sometimes have eager evaluation strategy. Some languages support some way to construct lazy data structures. So we're gonna study these kind of basic concepts in programming languages. If time permits, we will also look at type system and also mention a little bit about the implementation, but very mathematical sense. So there is a way to implement the call by name programming languages by so-called lazy evaluations. Sometimes it's graph reduction and so on. And we are not going to talk about its exact how to do this implementation exactly. Instead, we will provide some mathematical formalizations which captures the core ideas behind this implementation. But throughout the course, the main emphasis of the course is these programming languages are highly sophisticated objects which embodies many interesting concepts as well as implementation techniques. And the main objective is to analyze all these things in these programming languages mathematically. So that means we're gonna study quite a bit of the mathematical tools. So you will hear quite a bit, many concepts that coming from something coming from category theory, something coming from universal algebra, and some group theory and so on. But as I said in the beginning, we are not going to look at the deep theorems of these mathematical concepts. We'll look at some of the non-trivial theorems, but our main objective is how to use these mathematical concepts and tools to define what's really going on in programming languages and analyze its behavior and their behaviors. So let me give you some illustrations, some preview on what we're gonna cover throughout the course. So the first thing we're gonna study is the syntax. Okay, so if you think about the syntax of a programming language, you might say, oh, it's obvious. I mean, it's something that you learn in most languages. And you may think that the syntax is just a sequence of characters. Okay, so some sequence of a character form a legitimate program. Some sequence of characters do not form legitimate programs. So that may be one answer, but that's not the kind of answer we're gonna look at. That's because if we want to carry out the formal study on programming languages, this perspective of viewing syntax as a sequence of, just some legitimate sequences of characters does not really, does not really help us to, sorry, because I was keep getting interrupted by this request for to giving permissions to students who just to join this session. So there will be some disruption, now and then, that I hope you understand this. So the bad answer is a sequence of characters because this does not really have any structure and makes formal analysis very complicated. So instead, what we're gonna look at is, we will look at a program as an instance of an abstract syntax. So this is not about mathematics, or meaning of the program. It's more about what are these objects that we write as a program. Can you view it in a bit more abstract way so that we can deal with it more easily using mathematical tools? So more precisely, we're gonna look at the syntax as an initial algebra from the universal algebra. And then we will view each program as an element of the initial algebra. And this will help us in multiple ways. First, it will simplify, it will allow us to avoid many details about the syntax of the program, which are not very relevant for our formal study. The second, it will also justify some ways of defining functions on programs and so on by structural inductions. And because this initiality is essentially the same thing as saying we can have some induction principles on programs. So that's the first thing that we're gonna consider. The second thing we will consider is, is a domain theory. So another big theme of the course is the semantics of programs. Some tools we will develop, what we will use to define the semantics of program is a domain theory. So the domain theory is used when we try to find a mathematical meaning of each program. So for instance, you can see the Python program that I wrote on the top, which is defining function f, which take an argument g, and it just return an argument. So it's an identity function. And so if I ask you what does a function this f means, you can just say, oh, this is an identity function. So it may be it looks like it's very simple, but it turns out it's not. So yeah, it's an identity function, but it turns out it's not. That's because in Python, you can do something very strange. You can apply function f to function f itself. Okay, so then it's a legitimate function application. And then in Python, you will get the output is another function, which is the same as the function f. And that's kind of when you do the print, this is the output that you get in the screen. But now if you take a step back and think about what's really happening, we said this capital F define an identity function on some set D, or some D from D to D. But because we should be able to apply this identity function on itself, in some sense, D should include this function space as well. So let me use the screen. Cool. Yeah, so we apply the for the function f, we apply another function f. So in Python, what you can do is you can apply this function f to essentially everything, including the function space. So if I want to define the meaning of this function f, I first have to clarify what this domain D is, because it's an identity on D. But this D should include the function space itself, because the functions can also be applied as an argument for this capital function f. Okay, so this is not an exact notation, but we should have something like mean, legitimate argument should include function on D itself. Okay. But if you study the set theory, okay, so in set, there is no set D which includes function space on itself. So, I mean, there is one set which is if the set D is a singleton set, so then in some sense there is an inclusion from the function space to itself because this function space is also a singleton set. But if D is not a singleton set, nor M, I mean, D is not a singleton set, and this relationship will never be true. And that's one of the things that you prove when you study the set theory. But that's what's really happening in the programming languages. So in programming language, you can define a function f that can be applied to any functions in the programming language. So that means something interesting is going on in programming languages. And in fact, domain theory is developed to account for this type of phenomenon. And in domain theory, let us give a semantics of programs more precisely. And in domain theory, D is something called the domain, which is a set together with some extra structure. And then in domain theory, instead of thinking about all the functions from D to D, we will think about functions from D to D that satisfy so-called continuity property. And this continuity is closely related to the continuity from topology, but it's some way, it's not exactly, but it's some approximations of computability. So really, we are thinking about functions from D to D that can, in some sense, implementable by programs. If we do so, then we can give a meaning to this type of function f. That's what's going to happen when you use the domain theory. So this is another thing that we will study. The third thing that we will study quite a bit is an evaluation model. So think about another Python function f, which take an argument x, and then it just add x with itself. Okay. Now imagine the function applications where, yeah. So imagine a function applications f where we apply f twice to the argument 3. Okay. Now look at this entire expression from the perspective of outer f. Then from that perspective, then there are two ways of going about this evaluation. The first way of doing the evaluation, I mean, evaluating this application of the f twice on 3 is first to evaluate this inner f of 3. Okay, so evaluate this guy first, and then get the result. And the result is going to be 6, and apply the second f. So that's going to be 12. So that's one way to do it. So how the system does the evaluation. The second approach is, so this is 1 and 2. Second approach is don't do the evaluation of this f of 3 first. Instead, you just apply f directly to unevaluated expression, which is f of 3. So this outermost evaluation happens first. And then whenever it is necessary to see the value of the arguments while evaluating this outer f, then that's the time we're going to do the evaluation of f of 3. Okay? So this is sometimes called the lazy evaluations or normal order evaluation. This strategy that I explained first is called the eager evaluation. So, and in fact, I mean, which one is right is not firmly determined. I mean, there are programming languages that implement both strategy. So if you evaluate this argument f over 3 first, and that's called eager evaluation, there are programming languages that implement eager evaluation, such as Python, OCaml, Scheme, and so on. And in fact, I think most of the programming languages that you are familiar with will implement eager evaluation. But there are also well-known programming languages that implement normal order evaluation or lazy evaluation, where when we do this apply function f twice on 3, it doesn't really compute this argument f over 3 first. Instead, it just computes the outermost evaluations, and only when it's this evaluation really need to know about the value of the argument, that's the time it's going to evaluate f of 3. And that's called the lazy evaluation or normal order evaluation, or sometimes called outermost evaluation. And that's implemented in Haskell. And in fact, some programming languages like Scala is usually the eager evaluation, but sometimes it allows us to the lazy evaluation. Okay, so you can see that this is a kind of choice that's made by different programming languages in a different way. And that means because each of them has a cons and pros. Okay, something good and something bad, each of the options have. So we're gonna analyze these type of things. And just to show you, I mean, at this point, you might wonder why we want to do this normal order or lazy evaluations. But one way to see this is that, I mean, if you think about the function f, which doesn't evaluate argument x at all, and just return the 3, then if we do the eager evaluation, it's gonna call function f twice, because to get the value of inner f of 3, you have to call this function f that will return 3. Then to get the outer, you also have to go call f of 3 again, and that will return 3 as well. But if you do the normal order evaluation in this case, the evaluation will happen only once, because when you compute this outermost f, okay, when you compute this outermost f, the evaluation of outermost f, it's not going to use argument at all. So the evaluation of this inner guy is going to be skipped in the normal order evaluation. And in fact, this, I mean, sometimes called this lazy evaluation, is more optimized than the simple normal order evaluation. So from mathematical perspective, this lazy evaluation is the one which does the fewest computation. But that doesn't mean that it's the one that's the most efficient, because of some other issues with the, I mean, various issues with the computer and computer architecture. Okay, so there are these type of concepts, and we will analyze both this eager evaluation and normal order evaluation using operational and denotational semantics. And we will see some of the properties about this normal order and this eager evaluation. So that's what's gonna do in the course. Okay. So next thing, if I hope I can go to the type system this semester. I always didn't have enough time to do it, but I hope this becomes possible. And the last bit that I'm gonna want to talk about in the course is a type system. So this is again Python code. In Python, it's an untyped programming language, but you can do the typing by importing some library. Okay, so there's something called typing library. If you include the typing, something called callable from typing, then you can write the type annotations from function like this twice, which take function f as an argument and another x, and then what it does is that it apply f twice on the argument x. So it really just apply function twice. So that's what this function is doing. And in the usual Python, you are not going to write any type annotations, but in specific version of the Python, or if you use this library, you can write type annotation. And this type, I mean, the reason that people do this, I mean, actually in some programming languages, you always have to write type annotations. And the reason that the people do this is because that types will help people to develop correct programs. Okay. So, I mean, if you make some mistake, so instead of, I mean, passing instead of call, right, if you write programs like f of true, and that will generate a type error in this case, because the function f is supposed to be applied to the integer, but you're applying it to the Boolean value. So if, I don't know how many of you have used OCaml or some functional language with type system. I mean, type system is super powerful. So according to my experience, if you write OCaml program, which is type correct, in most of the cases, the program behaves as you expected. So types really help to check or detect the errors in the program. But then we may ask two questions. But types ask two questions. The first question is, can we infer these types? Can we always have to write? The programmer always have to write these type annotations, or can we infer these type annotations automatically? So that's the first question. And this is important because types are good, it's really helpful, but writing type annotation is a bit of a work. So if there's a system that infer these types automatically, that will help us to enjoy the benefits of type system at the same time without paying really the price of this writing type annotations. So that's our first question. The second question is, now suppose we wrote types or the type inference algorithm inferred types for our program. But then if you want to analyze the behavior of the program mathematically, you may ask, okay, what are the types? What mathematically? Types are, you can say it's a syntactic object that program use to detect the errors. But if we can actually go a lot more than just this superficial answer and try analyze this mathematical meaning. So one thing that, again, if time permits, I'm going to explain to you is that I would say types will be formed so-called partial equivalence relation of per. And so that captures two aspects of the types. And then for the first question, we're going to study a little bit of the type inference algorithms that will help us, they help us to enjoy the benefits of the type system without paying too much price for writing type annotations. But to give us some kind of maybe a bit of a hint about what this partial equivalence relation means, what it really captures, it actually captures something quite interesting. So if you write a type annotation like this, typically you expect that this, if you write type annotations, expect that will ensure well, not ensures, that allows to detect, well, it prevents errors in the implementation of twice. In other words, what it does is that it restricts implementation of twice. Okay, so this is what people typically expect when you see the type annotation. But types actually play, this is one role of the type. Type has a dual role, which is that it also prevents incorrect uses of twice. So if you have some program, so P, which somewhere it uses equals twice inside. So if once you write type annotation like this, this means that whenever you write program P, this program P should respect the type annotation of twice. For instance, we can't really apply this twice function to Boolean true, even though this may make sense if say for f is an identity function. Okay, so this is a kind of things is not possible in the type system. So that the first rule is about restricting the implementation of type. The second rule is limiting or restricting the clients or the uses of the types. So that's why we have this partial equivalence relation. So this is an equivalent, visually, if you have some x, partial equivalence relation means it's a subset together with some partitions of that subset. Okay, so it's a subset together with the partitions. And this subset corresponds to this number 1. So so this x is you can think of it as all the possible implementations. The subset means that we are only considering some implementation, which of twice, which respect the type annotation. This partial equivalence, this equivalence relation in this subset means that now when client uses the twice program, because it's using this twice in a very limited way, it sometimes can't distinguish the difference between two different implementations. So it will induce the equivalence relation on on the implementation. So that's what this each equivalence class really represents. Okay, so I don't expect you to understand all the things that I'm saying, but I'm just telling you, and this is a kind of I want to give you some feeling about what the course is about, and this is a kind of story that we will develop in the course. Okay, so these are the list of topics that we will cover in the course if time permits. Okay. So the first topic that we will look at is a predicate logic and simple imperative language and so on. So the first 5 topics are about the imperative languages. So we'll study predicate logic, imperative language, and essentially whole logic, as well as some extension about the imperative language with various features like a continuation, input, output, and so on. Okay, so that's the first part of the course. And roughly, we will cover all these things until a little bit like 1 week before the midterm exam. So we are not going to have a midterm, but until 1 week before the midterm periods. The later part of the course is about the functional languages. So we'll cover lambda calculus, eager functional languages, continuation in the functional language, normal order reduction, normal order language, and the simple type language. And then in the middle, we will study the 2 things, which is mathematical tools. They are about the category theory. That's because in the later part of the course, maybe blue is better. In this later part of the course, we will study the so-called recursive domain equations, something. So it's of some space D, which is isomorphic to its own function space, plus something like this. So this is related to the motivation of the domain theory that I told you. And we want to construct some space D, which includes its own function space. And then to do so, we will have to use some tools, mathematical tools coming from the category theory. So that's why we are covering these 2. And this type of equation will appear many times when we talk about this, discuss the later part of the latter part of the course. Okay. So the course webpage, I maintain the GitHub webpage. So this GitHub webpage will contain all the lecture notes of the course, as well as many important announcements. So essentially, you have to check the 2 things. One is this GitHub webpage, as well as KLMS. So in KLMS, through KLMS, you will see the homework exercise. Also, you have to submit your homework exercise and project and essays and so on. But this GitHub webpage will contain the lecture notes and other important announcements. And then although today I'm using this slides, all the lectures will be essentially a blackboard, which means I'm gonna use this handwriting programs in these online lectures, and then I'm gonna explain some concepts, mainly using my handwriting. And also my notes are also handwritten notes. They are scanned, and then I will make them available in the course webpage. And then the evaluation of the course will be based on the 3 things. Because it's a graduate course, I will just trust you. So if you don't feel like, oh, you can understand everything by looking at the lecture notes, or studying the textbook for yourself, it's okay. You can just do it for yourself. You don't need to attend this course. So I'm not going to do the attendance check. But in the homeworks and final exams, will use some of the things that I will discuss or explain in the lectures. So the 40%, we were not going to have a midterm exam, but we will have a final exam, which will account for the 40% of the entire credit and the entire marks. And then the homework, that I'm expecting there will be 4 homework problem sheets, but it may be one more or one less. So we will have a homework problem sheet, which will account for the 30% of the whole marks of this course. And there will be 2 critical surveys. I used to say 2 critical reviews before, but I changed it to change this nature of this critical surveys a little bit. Okay, so beforehand, in the previous year, it was about reading some assigned articles and then write us reviews about those articles. But this time, I changed the format a little bit. So now I will assign some topics, and then you have to study the topics for yourself and write what the topic is about and your critiques and so on about them. So let me explain a little bit about each of these, especially the final exam and the critical surveys. So final exam will be 10-hour take-home exam. So actually, you can see the submission box in the KLMS for this final exam and those 2 critical surveys. And the exam will take place at 10 a.m. on the 12th of December, which is Saturday. And from 10 p.m., it's starting from 10 a.m. until 8 p.m. So you will be given about 10 hours. We say exactly 10 hours to solve these homework problem, this take-home exam problem sheets. And then the exam paper will be distributed in KLMS. And then you have to submit your solutions in KLMS. And we are not going to accept any late submissions. So if you're late, then that's it. You get 0 for the final exam. And it's all done automatically by the KLMS system. And then the other important bit, which you perhaps are not quite familiar to you, are 2 critical surveys. And then this critical survey is about a study on assigned topic for yourself. And you have to write a review up to 3 pages, excluding bibliography. Okay? So you don't have to write like a 10 or 100-page report, so 3-page reports. But what I'm expecting is that it convey, many things that you learn about the topic. So I expect you to show your understanding about the topics. Also, I expect you to show that you really thought about the topic for yourself and try to analyze topic in your own way. And maybe you try to connect it with some of the concepts that you studied before and so on. So I'm expecting, so that to get the full marks for each of this critical survey, you have to go beyond the simple survey. And the marks that I'm gonna allocate is that I'm allocated 20% for the clear writing. This is, after all, this is a survey, and it's something like an essay assignment. So if your writing is not very good, it's not really ideal. So we are assigned the 20% for the quality of writing or presentation. So you don't have to be like some fantastic writer, but it has to meet some standards of the technical writing. And also for 40% of the marks will be assigned to the level of understanding that you demonstrate in your write-up. And the remaining 40% will be allocated for the level of originality shown in the report. So that originality will include, can be your own thoughts, connection with other peer concepts, in-depth some case studies or spin-off studies for yourself, and so on. So then there are 2 topics that I assigned for this critical survey assignment. The first, the deadline is the 30th of October, which is 1 week. So which is 1 week after the midterm exam. And the deadline is it's essentially a midnight, but I can't set the midnight deadline in KLM as well. So this is the 23:59. We will have a late submission policy, but there will be a penalty if you're late. Okay. The topic is something called the concurrent separation logic. And this is the topic, this concurrent separation logic is developed by Peter O'Hearn and Steve Brooks. And because of this work, they get the so-called Gödel Prize, which is one of the most prestigious prizes given for theoretical computer science. And then it forms the modern approach. I mean, it's not exactly the state-of-the-art approach for proving concurrent programs, concurrent or distributed programs, but it forms really the basis, where it really started the modern new approach for proving the correctness of concurrent programs. And if you go to the course webpage, I added a list of references that you can have a look at it. So there are primary reference, which essentially by Peter O'Hearn, which introduced this concurrent separation logic. But there are other kind of related materials there, which you can have a look at it and so that we can understand this topic much better. And I also included the potential questions. So I don't mean that you have to answer those questions. It's more like these are the kind of questions that you can ask. So ideally, if you form your own question and try to answer those questions, that's the idea. So in one of the, maybe not this course, but similar kind of exercises that I did before, some students really want, I think that students work on the complexity theory. So he analyzed the assigned topic from the perspective of complexity theoreticians. And that was actually a very nice essay. So you can put your own angles or your spins on this topic. So that's the first topic of the critical survey. The second topic is the relational parametricity. So this is, I don't know how, maybe I think all of you knows about polymorphism in programming languages, which means that the one function can be applied to the multiple different types. And there are two types of polymorphism. One is called Edo polymorphism. So this is instance of Edo polymorphism. Polymorphism is operator overloading. And then there is another type of polymorphism, which is called parametric polymorphism. So typical example of this is generics in Java. But also the polymorphism that you see in functional language like OCaml or Haskell, it is the parametric polymorphism. Actually, another instance of Edo polymorphism is Haskell type class is another instance of Edo polymorphism. So the idea of Edo polymorphism is you just put multiple different implementation together and give the same name, and then runtime system pick the right implementation based on the type. Okay, and then the parametric polymorphism is different. You have only one one uniform implementation that works for multiple different types. And then so these two guys are very different beasts. They have the Edo polymorphism is you just put multiple different implementation together and runtime system pick one. Parametric polymorphism has only one implementation that works on multiple different types. So they have many different properties. And then also they can have many different, they have a different mathematical formalization. So people in the theory of programming languages, working in the theory of programming languages, they develop a mathematical theory that captures this parametric polymorphism. So there are two mathematical theory, one sometimes called Strachey parametricity. The second thing is called relational parametricity. So Strachey parametricity is related to so-called realizability model. And the relational parametricity is developed by Reynolds. This is the author of our textbook. And then the Wadler also worked on this. And then many others. So, And then this relational parametricity, I can say, I mean, this is one of the, in a sense, nicest theories that's developed in the programming languages that may potentially have have some influence in the development of even mathematics and so on. It captures the idea of uniformity that happens in the programming languages. So the second critical survey is about studying this relational parametricity. This is a quite mathematical topic, but it's just, in some sense, one of the kind of most nice theories in programming languages. Again, if you go to the course webpage, you will see a reference, which references for this topic. Also, there are some questions that you may think about when you study this relational parametricity. Okay, so, and this is, something that I want to say. We will adopt very strict honor codes for handling plagiarism and dishonest academic behaviors. And students will automatically get F if she or he is bound to copy text from papers or books without paraphrasing them properly. Okay, so especially for undergrad, even, in the past, I noticed undergraduate students, as well as the beginning graduate students, they care a lot less on this issue of plagiarism. Okay. This is very, very important. In the places that I worked in before, some students was excellent. He did very good marks in the exams and so on, but he got, he almost failed. So in that system, students fail a year, almost failed because he copied a text from a paper without really paraphrasing it properly. So this course will have a bit like an essay exercise. These critical surveys are like essay exercises. And in those reports, if you get caught in the plagiarism, you will get automatically F. Of course, we will we'll make sure that there are no disputes about this. We'll perhaps run some system, the computer programs that will detect the amount of overlap. So make sure that you are not really cut and paste. Also, when you even write down what you learned by reading a paper, avoid looking at what's written there and just express what you learned based on your understanding. Okay. And the second is more familiar to you. If you are found to cheat in an exam or copy answers from or codes from friends or other sources, you will get F automatically. Okay. So for this, I announce this and then I make an announcement many times in the course. So there will be no disputes. If you are found to do this cheating, it's F automatically. There's no afterward discussion about this. I'm sure nobody is gonna do this, but I thought it's important to make this clear. And this is a final slide of today's lecture. And then so I'm Hong Seok Yang, and my office hour is actually, I didn't write the date. It's 6 p.m. to 7 p.m. on Monday. And you will see the information about my office hour in Zoom in the KLMS. So you can find information about this. And also Hyungjin and Dongwoo are going to be the TAs for this course. And they will make information about their office hour available in the perhaps a KLMS as well. Okay, so that's it for today, and we're gonna study the topics more seriously from the Wednesday. And I'm gonna stay here maybe 5 more minutes until 55. So if you have any questions, you can ask me. You can ask me questions about course logistics or maybe any other things. Okay, so that's it for today, and thank you all for coming.